And without further delay, welcome to Trenchless Designs and Risk Mitigation, the first webinar in a series of 4 provided by the Alliance for PE Pipe, along with W&L Plastics and Core & Main. Please note that this is a sponsored event and any opinions expressed are those of the presenters and do not necessarily reflect the views of ASCE. ASCE also asks that presenters and participants refrain from discussions surrounding competitors and pricings of products and services. And now it is my pleasure to welcome back for the 3rd year of providing valuable HDPE sponsored webinars with ASCE, Peter Dyke, Executive Director of the Alliance for PE Pipe. Welcome.
Hey, Robin, great job. Thank you. It's great to be back for another year with our colleagues and friends at ASCE. Robin, you guys do a great job. So to you and your colleagues, Sean Scully and others at ASCE, thank you for giving us this platform and sharing our knowledge about HDPE pipe systems with your members. We have a great show today. Alan Ambler and Nick Strader have put together a custom deck that hopefully will answer a lot of questions on how you can mitigate risk in your designs using polyethylene, but also using some real world examples that these guys have put together to illustrate some of their points. We have about 60 content slides to share today. So we're going to be moving really very fast. We have a deep bench of experts to share their knowledge with you on anything polyethylene, whether it's related to this deck or not. So we have a lot of people to thank for allowing us to fund this event. These are the companies that are on the screen right now. We thank them for their support of the Alliance for PE Pipe and our continuous educational programs that we run throughout North America. We do post on LinkedIn and other media every day. We post videos, content, and also we promote events like this. So follow us on your favorite media choice and we will be there for you. We have a lot going on as it relates to webinars, trade shows, and road shows. Road shows are the physical shows that we do. So here's a list of where we're going to be over the next couple of months. We have another webinar in a week called AMA, Ask Me Anything. Yeah, we got that idea from Reddit. It's really pretty popular. Maybe not as popular as this one, but it is very popular. We get 300-400 people on that call. So join us in that. You can find it www.pepipe.org. Thank you, Alan. All right. The Alliance is also home to a lot of free resources other than the content you get in events like this. We have seminars that we can offer to you. Send Dan Landy an email and we can schedule a custom seminar for you. That's a Zoom event. Could be in person, I suppose. We also edit your specs for free. So if you are with a consulting engineering firm and you have a library of specifications, give us a shot at one of them. We'll do it in Word, do track changes. You can accept or reject whatever we recommend. We also have something that my team is updating for this year called the Engineers Package. Alan Ambler, come online and tell us quickly about this Engineers Package that we love to share.
Thank you for asking, Pete. The Engineers Package has a nice collection of very useful information for you. Searchable Plastic Pipe Institute Handbook on Polyethylene Pipe in PDF format. It also has typical drawings, both in AutoCAD and PDF format, as well as specifications, as you mentioned. Lots of insider's guide to HDPE vocabulary and other resources such as that. That'll be released in that searchable PDF for you as well.
Good. Thank you for that, Alan. Alan is one of our key speakers today. Next slide, please. So as you endeavor to build your library, ask for the Engineers Package. If you need questions, take a screenshot of this and you can get in contact with us at the Alliance or with our 2 sponsors today, Rusty Reeves from Core & Main and Richard Colassa from W&L Plastics. Both are very well known in the industry as being experts on all things related to polyethylene. So with that, guys, thank you very much for sponsoring this and sharing the cost of this webinar at ASCE and making it available for, we had over 1,150 people sign up for this show today. Special thanks to these organizations for sharing their knowledge as well as their JPEGs with us to create this deck. Alan? So Rusty Reeves and Richard Colassa, could you guys come on and introduce yourselves? I'll start with you, Rusty. Tell us a little bit about yourself and what you do at Core & Main and what Core & Main could do for the folks on the call.
Hey, thanks, Peter. And again, thanks for everyone for joining us today. Yeah, Core and Main, we're a waterworks distribution company. We cover coast to coast, over 300 branches and over 4,400 employees. And really like working with both the PE Alliance and ASCE for these webinars. I think we have some great content today, just like we have in the past. And again, thank you for inviting us into your office day and let us know what we can do for you. Thank you.
Well, Rusty, we appreciate your support. And one of the reasons we like to partner with you is we can bring the education and the knowledge and the specs, but your team helps deliver the products to the job site. So we'd like to think it's a full package. So thank you very much.
Providing the goods, you bet.
Yeah. And then now, Richard Kalasa, if you could come on and say hello.
Hello, everybody. Again, I just want to mirror what Rusty said about having us here today. This is a great opportunity. My name is Richard Kalasa. I'm with WL Plastics. I'm the technical sales director for this company, and we are a very large polyethylene pipe manufacturer. We started off in 2000 as basically a 50 million pound, and we've grown to almost 1 billion pounds of production for polyethylene pipe only. So I have a lot of experience. My history is I used to produce the polyethylene, and now I'm actually producing the polyethylene into pipe. So I have lots of background, especially on the chemical side. And if you do have mechanical stuff that you're doing or civil stuff that you need answering, I can help you with that in some degree. If I can't, I'll make sure I find the right person for you. Core and Main is a great customer of ours, and we work together to help the industry continue to keep plastics in these applications, and hopefully we'll continue to grow.
Well, if you're doing 1 billion pounds a year, Richard, I mean, we're producing pipe in a lot of markets, not only just water, but oil and gas. So the oil patch, natural gas distribution, that's all polyethylene, right?
Yeah, that's correct. It's not just water and sewer, but there are other markets associated with that, of course, yes.
Well, Richard, thanks for your support of the Alliance and giving us technical expertise as well. It's very much appreciated. Also, I'd like to introduce my key speakers today, Alan Ambler and Nick Strader. Alan, tell us a little bit about yourself.
Hi there, everybody. My name's Alan Ambler. I at one point in time ran the utility as the utility manager for the city of Castleberry. So I do have municipal experience out there. Anybody in the municipal world watching us here. But now I run my own business, AM Trenchless. We provide lots of good support for trenchless technology, pipe bursting projects, horizontal directional drill projects, slip lining projects, any type of trenchless project that you're really into out there for it. And I talk a lot about polyethylene with Peter Dyke here. So we've got a couple of great questions already. Just a reminder, if you're looking for PDHs or CEUs, at the end, we'll have a survey. Complete that survey, and then it'll automatically load up for an Excel spreadsheet for us to make that process of getting you your certificate that much easier. So every 650 plus on there, if you want a CEU, make sure you do that. So
great. Thanks, Alan. Nick Strader. Nick, welcome, author of many technical papers on horizontal directional drilling. Welcome to the program.
Thank you, guys. Thanks for having me. Yeah, Nick Strader. I'm the trenchless practice leader for Brierley Associates. Brierley is a specialty consulting and design group focusing on planning, design, and construction management for all manner of trenchless projects, pilot tube, microtunneling, and directional drilling, as well as tunneling projects. Thank you for having me.
Yeah, well, thanks for being here. I first became acquainted with your organization when we did the longest, deepest drill on record in North America, and that's that 54-inch diameter Miami Beach HDD that saved South Beach from flooding with sewage. Yep. So I guess you were involved in that job?
Yes, sir. And we'll show some photographs of that shortly.
Oh, good. Excellent. And then also we have a bench. So to reiterate what Alan said, you got any question, Dan Landy and Aaron David are heading up our bench with several other individuals that we're not going to introduce. Let's not take that time. But Alan, take it away, and I'll be in the background. And thank you to our guests for being here to learn more about HDPE pipe.
Great. So happy to be here. And thanks for that handoff, Pete. So we're going to show you one of the main things. And then Richard, if you want to come on to because I know you're itching to talk there. Heat fusion is a process as to which, when controlled at any location, either through extrusion, through butt fusion, electrofusion, the different ways that we have to fuse the molecules of high density polyethylene, when we control it, that molecule interface is going to be strong, as strong, if not stronger than the pipe itself. Why don't you tell us why, Richard? What happens?
Yeah, so as you can see in the first slide there, we have what would represent two sides of a pipe, which would be in crystalline form, which those little ovals are for. And then when we heat those those two sides up, we actually push those materials into more of an amorphous state. So they open up and they go to their natural relaxed state. And then once we push them together in that fusion, there's not really any true mixing, but they do come in contact with each other, these interfaces with the conditions that we represent, and cool them again. You go to a solid crystalline structure again, moving up to about 60 to well, it's a little bit more than that. It's about 75 to 85% crystalline structure. So this is why we have a monolithic system. So then when we have these pulls and these trenchless situations, we really don't have a so-called joint. We have it's monolithic, and it's just one continuous run of pipe. So the strength of the pipe just becomes a solid single type strength for that pipe.
Here's an example of it. If you want to talk over the video for us.
Yeah, you bet. So this is opening. The heater plate's going to come out. You see a little bit of smoke there, but that's okay. The surfaces are very smooth. The heat beads are very nice and even all the way around, and we're going to push that together, and you're going to see the rollback. If you saw any kind of concave surface on that surface, you'd stop that process, because that means it was heated under pressure, and you were actually pushing the material away from the cushion of the molten interfaces. So as you can see now, the bead is very even all the way around. That's an indicator that rollback and the pressures that are being used are acceptable for that joint.
So that was shot, Alan, at Fort Lauderdale, when we helped the utility save the day when they were in an unplanned manner flooding the intercoastal waterway with sewage. So polyethylene saved the day, and that's where I got that image.
Gotcha. It didn't take Pete long to pop back on and have a comment there. That's perfect. So this process is repeatable. And out in the field, if you get to an oops or something of that nature, you don't necessarily have to use another fitting. You can just go right straight back through and change that. So one of the characteristics that's always the most amazing to me, Richard, is the changing viscoelastic behavior. So
right.
When we load this pipe with a duration of a loading, then we change the apparent modulus of elasticity, and that actually gives us some of the ruggedness, durability that we like to see when installing the pipe. But go ahead and tell us a little bit about that as well.
Yeah, so this is one of the areas I get a lot of questions on, because it's misunderstood in terms of how long it's supposed to last. But when you're pulling a pipe in through a trench situation or a HDD situation, or even a slip lining situation, you have to kind of understand what its resistance is, so you don't pull that pipe apart. And so you have to ask yourself, well, is it an instantaneous response like an H20 load? Well, then you would use a 150 PSI to evaluate that resistance to collapse or any kind of deflection of that pipe. But as you're pulling it through, you can say, okay, well, geez, I want this pipe under this load to last 50 years, and we would actually punish ourselves in terms of the modulus and use a lot lower number to understand the collapse aspects there too. So we really truly understand not only short-term response to installation, but also long-term response for the trench and the depths that you're putting that pipe in. And even for the Miami job that you're going to see on video, I mean, I believe that was 45 feet deep. You can correct me if I'm wrong on that, but there's some loads there that you have to take into consideration. So you want those long terms. And we actually have another one that's a little bit less than 29,000 for 100-year as well. So we don't have any collapse within that. So this is why this apparent modulus is so important. And remember, it's at 73 degrees. Okay, because if we increase temperature, that modulus is going to reduce. If we make it colder, it's actually going to increase. So we want to make sure that everything we evaluate is at that 73-degree mark.
Richard, they're asking some really good questions in Q&A about resin. So you're getting done over there to make sure you go and show everybody what the Q&A is.
All right, thank
All
you
right,
very
here's
much.
another example of being able to flexible, maintain or use the flexibility of this pipe. As the video shows, we're pulling it from lay down yard directly to the pipe insertion pit as we're looking at a trenchless project. And then you'll see on the right, again, we're lifting that pipe to be able to make sure that we get the appropriate angle to be able to get it inside of whatever excavation we're trying to get to. HDPE does have one of the most forgiving allowable bending radius of all pipe material. Interestingly enough, in pipe bursting and in horizontal directional drill, the limiter becomes the drill string more so than the actual allowable bending radius of the high density polyethylene pipe as well. When we get to thinner wall pipe, so the DR is inverted, a higher number is a thinner wall or a weaker pipe. We can overstress that pipe, which is what you'll see in this middle picture of kinking this actual pipe. And what the contractor did in this scenario is go beyond that allowable bending radius, and they'll simply cut it out and refuse that pipe and make sure that they protect the bending radius of that pipe as well. So Pete loves this video we got here as well. This is someone that really trusts the viscoelastic behavior of high density polyethylene, taking their Ferrari or Corvette or whatever that might be underneath that high density polyethylene as we go through. So the fusion process that we spent a few minutes talking to you about as well shows when we are making these cuts of the pipe in the field, it's very easy to work with it with a dry chainsaw or a sawzall, as you're seeing here, and then they will simply fuse that connection back to where they need it to go in that manner. So Nick, we'll go ahead and pull you on to talk about horizontal directional drill as we go through and really launch into the most popular trenchless method for installation.
Exactly. Yeah. So when we talk about trenchless, as the name implies, it really is going to be any method to install pipe or duct beneath some type of surface obstruction to reduce disturbance. And that may be a roadway or a river or a railroad. And one of the most common methods out there right now is horizontal directional drilling, also known as HDD. Next slide. So we use HDD a lot with HDPE pipe. It's a good marriage for all types of applications, including water, wastewater, as well as duct for both fiber and electric. Common drill paths with HDPE generally going to range, depending on the pipe size, anywhere from about 400 feet up to about 3,500 feet is pretty common. Pipe sizes, common pipe sizes are going to range from about 2 inches up to 36 inches, but there are exceptions. The picture in the middle of the slide, and Alan, if you want to run that animation, shows a 54-inch diameter HDPE pipe that we designed for Dave Mancini and Sons for the city of Miami Beach. Really big pipe. We actually have footage floating around of a drone flying through this pipe. 54-inch DR17 with a total length of about 4,200 feet. Next slide. So we're going to show a couple of slides depicting the HDD process. These are slides and schematics that were generated by Mears Group. It's really a 3-part process. And the first stage involves advancing a small diameter pilot hole from an entry pit to an exit pit. And this part of the installation is carefully designed in advance to accommodate the bending capabilities of the drill rods, the bending capabilities of the product pipe, which will be pulled into the hole, as well as the subsurface conditions. And during the piloting, the driller will monitor the location of the bit at all times using either a walkover wand or, for the larger installations, more commonly a downhole steering tool, which will be connected to the ground surface through wire lines within the drill rod. Next slide. Now, once we have the pilot geometry established, the contractor is then going to enlarge the hole through a series of push or pull reaming passes to the desired finished diameter. And that diameter, usually for bigger pipe or bundles, is going to be about 12 inches larger than the product diameter. Now, once the hole is fully enlarged and prepared, The contractor is going to attach the product pipe or the bundle to a swivel and then pull that back into the borehole, ideally as quick as possible. In most cases, we want to have the pipe or the bundle fully assembled at the exit to minimize any downtime, realizing that stopping the pull does add some risk of hole collapsing and getting the pipe bound. Now, it's important to understand with HDD at all times, the contractor is pumping a bentonite-based drilling fluid down the center of the rods out into the borehole through the drill tools, which will remove the cuttings. It'll stabilize the borehole, and it lubricates and cools the system, facilitating the drill tool advance and the product pipe installation. Next slide.
Hey, Nick, just a quick
Yes, sir.
question for online. Sorry, I need to interrupt you on this one, but what soil modulus do you use when directional drilling? Do you assume the native material surrounding the bore or take the drilling mud into account?
If we're talking about an IR analysis, we're looking at the modulus of the surrounding material.
Thank you very much.
Yep. Next slide. So we look at our typical HDD design. There are a number of common geometric components that we can see in this schematic. In a very simple form, we're looking and considering an entry angle, an exit angle, a total depth, and then the radius of curvature in our entry arc and exit arc, and possibly in the horizontal. So next slide. For the entry angle, people often ask, how steep can I enter the ground? And it's really going to be driven and controlled by the drill rig. Most rigs are not set up to drill any steeper than, depending on the rig, anywhere from 18 to maybe 22 degrees. And so the most common entry angles that we use usually are about 12, 14, and 16 degrees. Next slide. On the far end, on the exit side, the exit angle tends to be softer than even that. Even though we can exit steeper, need to keep in mind that the steeper we exit, the more difficult it is to manage the product pipe, which has to be directed and guided into the borehole. So typical exit angles are going to range usually from 8 to 10 degrees, maybe 12 degrees. You can imagine if we were dealing with a steel pipe, as we can see in the center photo, it can be very tricky and problematic to actually handle that pipe and direct it into the borehole without damaging the pipe or overstressing the steel. The nice thing, one of the nice things about HDPE is very forgiving, as Alan mentioned. It's very flexible, and usually it requires less equipment and less process to manage it into the borehole. Next slide.
So Nick, some of the most common failures that we see are trying to achieve a depth, a very deep depth as quickly as possible. And I think that the entrance and exit angle limitations are explaining why that's not possible, is because the equipment simply can't traverse quite a depth that quickly. That's one of the most causes of design problems that we see, is over stressing how quickly you can get down to depth in this. Is that correct?
Absolutely. We'll look at some drill steel limitations here in a second, realizing that, yes, maybe you want to get down to 40 feet over a short distance, but with these limitations, it's going to take you some time to do that, realizing we can't have a super steep exit or entry angle. In terms of the radius of curvature, getting into what's going to control that. With any HDD project, we need to think about how tight can we bend in the vertical and in the horizontal. And that's going to be governed by two things, one of two things, either the drill pipe or the product pipe. Now, all HDD drill steel is designed to bend, and you can see that on the right. This is drill steel at the ground surface, and the bending capabilities will depend on the steel itself or the drill rods themselves, and it'll vary by manufacturer. Maybe you've got a drill rod with a minimum radius of, say, 400 feet. You don't want to bend it any tighter than that or anywhere near that, because you run the risk of breaking the pipe off. We also have to think about the product pipe. If we're dealing with a steel pipe, it may be much, much more onerous in terms of the limiting bending capabilities. In a lot of cases with a steel pipe or steel casing, that will govern the minimum radius. One of the nice things about HDPE, again, it's very flexible. And in almost all projects, is not going to be your limiting factor in terms of your minimum radius. The minimum radius for HDPE is typically going to be the drill steel. Next slide. So these are a number of common reference documents. This is a good time to take a screenshot. If you're planning or designing an HDD project, ASCE MOP 108 for pipeline design by HDD, NESTT good practices, ASTM 1962 is a good reference, provides good guidance on evaluating pullback loads, the PRCI manual, and then the PPI manual for PPI handbook of polyethylene pipe. Next slide.
So just to tell you more about what types of tools that you have available for you as well, PPI has a bore aid calculator that's online that you can take a look at. And you could put those preliminary project design parameters into this calculator. Say you're at a 30% conceptual level, laying out where you think a drill might go, see if it's feasible or possible. And then they'll calculate, of course, all the different values for different sizes of pipes and lengths and see if they'll withstand some of the pulling forces as we look at that. Of course, these are a 30% planning level document. And then beyond that, you need to look to somebody like Nick to be able to come through and do your design. Or if you have competent engineers on site, they'll go through the iterations as well. So the Alliance does have calculators for you, but we want to know more about your project before just turning you loose on those to be able to make sure that our engineers on staff are going to give you some good guidance. So here's a little bit more from Nick.
Sounds good. One of the things we really need to understand when we're planning and designing a directional drill is going to be related to the subsurface conditions and the geotechnical parameters. And so the first thing we'll do is start evaluating what we think we're dealing with in terms of regional geology, looking at available references. What are we dealing with in terms of soil types and thickness, depth to bedrock, and groundwater? And then we'll go out into the field and complete some site-specific subsurface investigations, and then collect samples for laboratory testing, which will help develop geotechnical parameters for detailed design. Next slide. So the most common exploration for directional drilling, because of the depth, will be sample test borings. On land, we'll do these with truck-mounted or bombardier-mounted rigs. Over water, if the depth and current allows, we'll do these with barge-mounted rigs. So I commonly want a test boring at our HDD entry and exit, and then we typically will take these spaced out along the alignment, depending on access and the subsurface conditions, at a spacing anywhere from about 400 to 700 feet. And the test borings want to be drilled to at least our bore depth and then beyond, in case this needs to be lowered during design or construction. In soil, we'll typically sample every 5 feet using split spoons and or undisturbed tubes in cohesive soils. If we encounter bedrock, we can definitely drill in bedrock, but we want to sample that and know where it is and have some good laboratory testing. So we want to core that and then grout the test borings when they're done. Always save the samples through construction. Next slide.
Nick, another quick question. Can you combine the horizontal and vertical alignment changes for drilling operations?
Can you repeat the question?
Can you combine the horizontal and vertical alignment changes for a drilling operation? So if you want to move up or down or left to right as you're drilling through the path, can you use both of those directional changes in a single drill?
Yeah, so if we're talking about the directional drilling itself, you can. Usually we want to be turning and steering in one dimension and not both at the same time. You usually want to avoid a compound curve. But yes, you can. You can steer vertically as well as horizontally.
Thank you.
Yep. In terms of the subsurface characterization of what we're looking for, really looking for a lot of detail. So we can understand our penetration rates, understand what we need for drill tools, the cost of the bore, schedule, and the potential for risk, obviously. So we want to know the depth of the fill, which can contain obstructions. We need to know the soil gradation. Are we dealing with a clay, silt, sand, or gravel? What's the density of the materials? I want to know the formation type. Is it a glacial till or a glacial lake deposit? Because this will dictate ultimately the gradation and the behavior. We need to know the potential for obstructions, such as cobbles and boulders. What's our depth to water? How permeable are the soil and bedrock formations we're dealing with? And if we're dealing with rock, we can definitely drill use HDD and bedrock, but it is more time consuming and expensive. So we definitely need to know if it's there, how deep it is. And if we're dealing with it, we want to know the rock type, the hardness, the weathering, and the fracture patterns. Next slide. Lab testing, once we have our test borings done, we're going to submit samples for testing to further characterize and develop parameters for design. Most commonly, sieve and hydrometer testing for grain size, unit weight testing. If we have clay soils, cohesive soils, we'll be running strength testing. And then on bedrock, we definitely want to do some compressive strength testing, ensure sharp abrasivity. And next slide. Once we have all of our information from our background research and our test borings, we'll start putting together an interpretive geologic profile, which will help us optimize our HDD geometry, specifically intended to reduce our risk of frac out, which we'll talk about, reduce our risk of encountering obstructions or materials which may give us trouble, such as potentially shallow bedrock, cobbles and boulders, or clean gravel. Next slide. So in terms of workspace, the workspace required for HDD is going to depend on the size of the project and the magnitude. At the HDD entry, this is an example of an entry area workspace for a larger setup. You can see in the middle of the slide, we have a rig and drill rods and handling equipment. We also have a power pack, trailers, and what you can't see in the foreground is all the drill fluid processing equipment. It is going to vary depending on the magnitude of the project. Next slide. For smaller scale projects, it's going to require a smaller footprint, obviously, a smaller rig, smaller support equipment. This is an example of a roadside project where the workspace has been arranged in a linear format to occupy a smaller area adjacent to the pavement. Next slide. On the exit side, we're going to need room for a pit, pipe handling equipment, and then the product pipe. So very important to remember, if at all possible, we want to have the product pipe or duct fully assembled and laid out and ready for pullback once the borehole is done. You can assemble and fuse pipe as you pull it back, but it does result in more risk of getting the pipe bound. So if we have 1,000-foot long bore, ideally we want to have 1,000 feet of pipe fully assembled, tested, and ready to go in the borehole. Next slide. Another thing to be aware of are existing utilities. As with any trenchless project, we want to know where the utilities are in advance so we can design around them to avoid them, to minimize the risk of unnecessary utility strikes. And this involves more than just the utility one call. We're talking about record research as well as soft dig confirmation prior to drilling. Photograph in the middle of the slide is an HDD rig, which has just unfortunately encountered and struck a high pressure gas main. So we definitely need to characterize and know where the utilities are prior to construction. Next slide. Some specific risk considerations for HDD. Every trenchless method has risk. HDD is no different. One of the most common risks is inadvertent release of fluid or a frac out. And this is a situation where the drill fluid exits the borehole and gets to the ground surface or a water body. We'll talk more about that in a second. Other potential sources of risk may include heave or subsidence if we're dealing with a road or railroad. Clean gravel can be problematic, can be difficult to support. Can be difficult to get out of the borehole. Soft clay can restrict the borehole. Hard bedrock can be problematic in terms of penetration rates. Abrasive conditions in soil or bedrock can result in premature wear of tooling. Geologic transitions, if we're going back and forth from materials with dramatically different gradation or densities, can present challenges in terms of lots and lots of drill tool changes, as well as risk to the drill rods and the bits and the reamers, which can also in turn result in risk of tooling failure. Next slide.
So as I'm looking at this slide and your explanation, Nick, it summarized why we go through the whole process during design to identify these geological scenarios. Change along that bore path obviously needs to be understood by the contractor doing that work. We've had a lot of great questions about this concept as well, and it sounds from personal experience that you'd get in the field by encountering these conditions are really one of the best opportunities to learn from something. There's nothing like learning from failure. But when we do these webinars, it's sometimes easier to learn from somebody else's failures. That's why we try to help as much as possible. Just like to frame where we are, we're about 35 minutes into it. We've had over 60 questions, 722 participants. So guys, keep it coming. That interaction is one of the things that we really try to provide here with the Alliance for Pipes events. And we're very blessed to have Nick with us to share his experience.
Sounds good. Next slide. So specific to HDD is the risk of frac out or an IR. And this is, again, a situation where the drill fluid suddenly exits the borehole and reaches the ground surface or water body. It's important to understand that with directional drilling, there's always a risk of frac out. We can't completely eliminate that risk. We need to understand why it happens. As I mentioned before, we're always pumping drill fluid down the center of the rod out into the borehole, and then that's traveling back up to our entry pit or our exit pit, and that helps to remove the cuttings. But it does put pressure on the surrounding ground, whether it's soil or bedrock. We have a dynamic pressure from the pumps as well as a static pressure based on the weight of the drill fluid. So if that exceeds the confining capability of the ground, we can start to lose that to the surrounding formation. So as part of the design process, standard of practice is, again, to develop a detailed geologic profile, estimate what the downhole annular pressure should be for a given geometry, and then compare this to what we would estimate the confining capacity of the surrounding ground would be using a number of different models. And an example is shown on the right. There are a number of commonly accepted models to do this. The Delft equation is one, Queen's equation. We also use total stress. None of these are perfect models. It really is a matter of understanding the relative risk, where we think the risk may be, to get a feeling for what the contractor needs to plan for relative to potentially repairing the borehole or cleaning up an IR during construction. Next slide. So in terms of risk mitigation, I'll finish with this. We always want to make sure that we're designing within the standard of practice, so using appropriate design references. We always want to have a good geotechnical characterization in advance to understand what we're dealing with, and if at all possible, design to avoid that risk, whether it's cobbles or boulders, potentially problematic bedrock, clean gravel. So the design should address the geotechnical risk, should have an effort made to understand the risk of IR, make sure the contractor and the permitting agency is aware of that. We need to think about the potential risk to the tooling as well as the product pipe. HDPE, as well as any other product pipe, is going to have a limit in terms of the pull force and the buckling potential. And so during the design process, we also want to understand what the anticipated pull load is going to be, so we can select the appropriate pipe, as well as what the external loads are going to be. And we also want to think about the risk to the surrounding structures, whether pavement, utilities, or railroads, for instance.
Great job. I'd like to close with one question. A participant asked, Nick, should relief holes be used to control frac outs in unintended locations?
They can be. We've had situations where it does make sense to pre-drill holes to allow the drill fluid to escape, provided you can get to those and manage it. We've also had situations where once an IR begins to happen, it makes sense to let it bleed and control it, and you know where it's happening. So it can be. Like any other trenchless project or any other geotechnical situation, you're also assuming that it's going to flow where you want it to go. So sometimes they work, sometimes they don't.
Yeah. Hey, well, great job. And, we didn't really talk about the bentonite and what the fluids are, but the great news is most of this is just water and clay. Am I right?
It's environmentally safe, the same kind of stuff we use for drilling water wells. Absolutely, it's environmentally safe and no contaminants involved. Yeah, that's the standard of practice at the moment.
Good. Great job. If you could help us out on some questions, Nick, I'd appreciate it. Now we're going to talk about slip lining. Alan Ambler, take it away.
All right, so slip lining is another trenchless technology. What we are doing is we're taking advantage of the fact that we have an existing conduit, properly preparing that pipe to receive the new pipe, and essentially just using that to be able to protect that replacement pipe as we go through. So some key points we want to look at. We don't want any obstructions within that existing pipe or that conduit that would preclude us from being able to pull in a brand new pipe as we go through there. So we do evaluate the integrity of the host pipe because there's an option of having a semi-structural liner versus a structural liner. The difference there being the DR rating of the pipe that we're pulling back into place. And we are limited in our ability to be able to pull through those bends. So those are going to be spots as to which we would have an excavation and make sure that we pull through that location. Richard, yes, you'd like to add something?
Yeah, and it's really important that you do the preliminary work on these existing lines. I mean, we're showing you an old brick sewer line. We're showing, and there's lots of different things, but also just the space the space reduction you have for slip lining as well. So if you look on that picture on the right, I mean, the traffic is still moving as well, and you're putting in a significantly large pipe. So it's a good consideration, and it can be a long-term consideration. But if your pipe is going to deplete over the next 5 years, let's say through corrosion or whatever it may be, you may want to consider a DR that will be able to self-sustain the top loads for it as well.
Can you tell us what's happening in the video on the right here, Richard? I think you're familiar with that video.
Yeah, that was in Miami. That was just on the other side of the airport, the international airport. There was a whole bunch of sewer rehabilitation there. But the interesting thing about this one was the hole that was in the back usually uses a strap to pull that pipe into the existing line. But as we started to push it from the back, it went in quite a bit faster. So I asked the engineer, I said, well, is there any obstructions in that existing line? He said, no. I said, just push it in. Took him literally 3.5 minutes to push in about 250 feet of pipe. So it was awesome. And that's 54-inch diameter, by the way. So it was helped that process quite a bit.
That's it. So properly preparing the pipe, making sure there are excavations to access the pipe are shored properly to give us that preparation, and then fusing that long run in advance is going to give us some major productivity improvements as we're looking through it. So we've got less than 20 minutes to go and 77 questions that are answered. So keep going. That's just awesome, everybody that's out there. Compressive fit lining is another type of lining that actually only uses high density polyethylene. And what we do with compressive fit lining is we'll take a larger OD of a high density polyethylene pipe and put it through either a series of rollers or a die, reducing it to a smaller OD, pull it into that existing pipeline, and then allow that high density polyethylene to naturally relax and force up against that interior surface of that pipe. So yes, preparation is key on all this. And this really takes advantage of that viscoelastic behavior of high density polyethylene that we talked about previously. Yes, Richard.
Yeah, so and just from slip lining to compressive fit, this is quite a bit different, but the same. These particular annuluses that make people uncomfortable or engineers uncomfortable, that's a very common question. Well, do I have to fill in that annulus? And the answer is really no. If you've got exposure to huge temperature changes at the front and the back end of, let's say, 1,000-foot tunnel, and that space is in there, that pipe can float around in that empty space without. I know that the top loading, if it's H20 types of situations are there, but if you're confident in your existing pipeline that's casing that liner, that's great. But if you're not, then you can fill it with grout, and there's no issues filling it with grout, because I know grout cures at a little bit higher temperature, but we don't see any negative effects with grouting polyethylene as well. Whereas the compression fit will eliminate that annular space altogether. Thank you.
So you'll see in this picture, we've got a series of scrapers to be able to clean out an existing cast iron pipe. And then you'll see a foam pig. And that's a proving pig to make sure that once that pig becomes is retrieved undamaged, then we won't have any problems being able to put this new polyethylene liner within that pipeline itself. Here's a good schematic of what we're looking at. A 32-inch pipe is now becoming a 29-inch HDPE pipe under tension. This is a project in New Orleans. And then now we're pulling that through that existing pipeline, taking advantage of those molecular properties of HDPE in just a wonderful manner. Most of the time when I talk about slip lining with engineers, they are conservative and they're always asked, how can we get the largest ID of the replacement pipe if you're not going to pipe burst it? And this is how you would do that. So here's a video of it. Now the forces that are required at the ends where this die is very specifically are heavier than what you would see in a normal slip lining process. And in some instances, even heavier than a pipe bursting process because we're forcibly pushing that HDPE pipe through that die. So you would pour concrete or otherwise heavily reinforce the interface of the soil at that location to make sure that we're not pushing that die through the soil column as we go through. So here's Rusty, you want to come on and talk about some final connections and what Core & Main can possibly show us for how we would connect this to other pipe materials or high density polyethylene in the intermediate.
You bet. Yeah, it's always key to be able to do these tie-ins, particularly on these trenchless projects, but you even have it with others, even with repairs. But we actually have a full line of in-ditch fusion equipment. That's always going to be my first choice. Fusion for polyethylene is the #1 connection that you want to try to use. We have machines that you either take the carriage off and can drop it down, or this particular photo is showing a specialty in-ditch machine, and we can go up to 63-inch on those, and we have those in stock for rental or to have us come out and do the job. But the next thing would be possibly an electrofusion coupler. That's always a good backup as well, and is basically just hooked up to a smaller box. You manipulate the pipe into the coupler, making sure it's centered and properly prepared, which would take some scraping and that type of thing. And then you just cook that coupler, and it will do the same thing and give you a good joint. So there's a variety of things you can do. There's some mechanical as well, but in my book, fusion's always going to be #1, electrofusion 2, and mechanical coupling after that. So.
Awesome, Rusty. So for an electrofusion coupler, they have embedded copper wires within it that generate the heat. And then when Rusty talks about scraping the surface, what we're doing is we're removing the oxidative layer on the outside of the high-density polyethylene to get back to that pure resin that we showed you in the very first series of images for what happens to high-density polyethylene through heat fusion. So when I talk about controlling the environment, those are some of the steps that we go through for electrofusion. Perfect,
So
Rusty. Thank you. So,
yeah, that scraping would be similar to the facing on a fusion machine. Yep, exactly.
Absolutely. Wonderful. Now we'll talk about pipe bursting, which I've done quite a bit of in my time and my experience. There's two primary types of pipe bursting. For start, pipe bursting is the only trenchless technology rehabilitation method that can put a larger OD pipe back into place. Everything else is going to have a constricted ID, even cured in place pipe lining or spray epoxies as we go through that. But pneumatic pipe bursting only uses high density polyethylene, and that's because it takes an impact hammer and inches it along that pipe, and that constant motion and stress is absorbed by the high density polyethylene with no detriment to that pipe material. Static pipe bursting can be primarily used for waters. You could seal off the ends of the pipe and nothing goes through it. And pneumatic pipe bursting, an air compressor pumps through a air hose, delivery hose to the interface right at the impact hammer as it goes through. So here's a schematic itself of pneumatic pipe bursting. We are using a constant tension cable winch to be able to make sure that that impact hammer face and the expander head is aligned with the existing pipeline, and then it just inches through as we go forward through that. Here's a couple of images of fixing an expander head to high-density polyethylene. It is robust enough that they simply just screw those screws into the side of the high-density polyethylene, and it grabs on, that expander head grabs on into the high-density polyethylene itself. itself. After they've made the pull, then they'll over pull and cut the section off. It's very common to see it. In this particular image, you'll see a lubrication port on the side as well. They were expecting excessive friction along this pull, and lubrication, similar to a bentonite, can be used to be able to make sure you reduce those friction forces as we go. Richard.
Any problem with bursting AC pipe?
That's a great question. Asbestos cement pipe can be burst under existing regulations. It is legal. Now, the people that are tasked with enforcement vary throughout the country, and good messaging needs to be provided if they are otherwise unfamiliar with AC pipe bursting. Most of the guidance has been given for vertical construction instead of buried asbestos cement pipe. So they are bursting in state of Florida, Michigan, Texas, and even in the heart of environmental country with the Bay Area Air Quality Management District. My company, Trenchless, has helped make sure to facilitate that. If you need a primer on AC, way more than that, definitely email me and we'll provide that contact for you. Here's a video simply on an advance, and you can hear the knock as it goes through of an impact hammer coming through a pre-dug excavation for service connections as we look at that. That's all it is, just inching along as it moves through that, pushing that pipe into the 2 to 3 inches of soil surrounding that replacement pipe. So here's static pipe bursting. The change in how we deliver the force is the only difference. We're using a hydraulic power pack to push through a static bursting unit and that series of rods as you go through. So here's an advanced quick of high density polyethylene replacing asbestos cement pipe. See, we are making sure that it's wet and all the fibers stay suppressed and in the excavation it goes through. And you'll see an extraction cage here to remove the tooling and equipment on the face of the pipe bursting expander head there in that manner as well. Here's an additional video that I'll talk through, basically of fixing that expander head onto the pipe bursting or high density polyethylene. This is done with a swivel rig instead, and you'll see that you have a series of cutters on top of it. Once that excavation is done, we'll make sure to put it in the hole to be able to come through and perform that pipe bursting rig. Now we'll see, I liken the excavations required for shallower pipe, existing pipe, as surgical excavation in urban and suburban areas. Now we'll get through on a 1,000-foot run. If you have that much to go through, you'll excavate the valves and the service connections. A 1,000-foot run, you can actually minimize your excavations to about 40 feet. So when we talk about 85% less trench, that's what we're really doing. Here's examples of pipes that can be burst. It cannot be burst if we're going to have a pre-stressed concrete cylinder pipe or some other type of reinforcing through it. Every day of the week, cured in place, clay VCP pipe is burst. Cast iron pipe is burst. Now, when we get into ductile iron or corrugated metal pipe, then it's a bit harder to go through that process. Yes, Richard.
So just another quick question that I emailed, but for steel pipes, we can use a special cutter for those, correct? If need be, and it's not really bursting, it's cutting it?
Yes, those are pieces that are done in advance of a static rig and in advance of the expander head. What you're seeing here on the left video is just AC pipe fragments that stay within the soil surrounding it. And what you'll see on the right here now becomes cast iron as it's burst through. In static pipe bursting, we can put slitters, as Richard mentioned, or cutters or other things that'll shear the existing pipeline as we go through it as well and move along. So here's a pre-stressed concrete cylinder pipe. So when we get that typical cross section of the pipe that has a bunch of reinforcing in it to resist both compression and tension, now we won't be able to cut through this material to be able to burst it. That's when we compressive fit line it or slip line it as we go through. Here's a classification chart is put forth by the International Pipe Bursting Association. It shows degree of complexity as we go through to be able to move to developmental projects such as the ductile iron pipe or the corrugated metal pipe that I talked about. There's excess risk in that needs to be shared with the contractor, and they will determine whether or not they feel up to being able to perform that type of a pipe bursting project. Now, since we are taking advantage of a proven conduit location, we know it's generally free and clear of third-party utility conflicts. What we want to look for is the existing trench condition, if it's the diameter and then some of the pipe to be able to allow that expander head to go through, or if that existing trench was excavated on rock or stiff to hard clays. Those are going to make it so most of the expansion forces are go up, or we are not going to be able to push the expander through that as well. Here's some soil displacement as we look. Here is simply just taking a 4 size upsize. So that's 16 inches from the original 8 inches. And as you can tell, we are displacing quite a bit of soil in that manner as we see this here. So this is important for high density polyethylene. The industry itself has tables of safe pulling stress. So that's important when we compare friction along a horizontal directional drill, or if we want to try to estimate friction forces in pipe bursting, which is actually a fairly challenging thing to do. If you're interested in that, make sure you look at our more advanced pipe bursting webinar to be able to talk through some of those points itself. But this varies because the viscoelastic or the modulus of elasticity of that pipe varies with time. So I'm showing you a 1 hour safe pull stress and a 12-hour safe pull stress based on DR11 or 17 in various pipe sizes. So we would look at that to be able to make sure we gauge our safe pulling stress. So an interesting thing about taking advantage of that third party, existing conduit is the being free from third party utility conflicts, and we generally have a good path already established. Therefore, in some instances, when we share risk, the owner understands the process. We can take advantage of little less design work up front. This is a key difference between horizontal directional drill and pipe bursting. In fact, I've designed over 42 miles of pipe bursting projects from GIS records itself. Part of that is to require a bid plan, or not a bid plan, but a burst plan from the contractor to show that they've thought through the process required to burst the project and have good construction observation on the opposite side. So high density polyethylene does have a gouge allowance that if you gouge 10% or less of the pipe wall thickness, then it operates with a normal life of itself. So that 10% can be hard to guesstimate through it. So I say, when in doubt, cut it out. And we'll show you some examples here. Pipe scraping or gouging, that is okay. You could see here, these are just surface scrapes that are pulled along a roadway to move it from the laydown yard to the actual pipe insertion pit location as it's sent. And I didn't have an example, it seems, of a bad gouge as well. So that would be obvious that it's a bad gouge, 10% or more of that wall thickness. And again, when in doubt, cut it out. In many instances, that foreman that's doing the pipe bursting project can easily make that connection, cut it out, and then refuse that location in under 30 minutes, depending upon the DR and the size of the pipe. So every pipe bursting superintendent out there knows that they may have to dig an unplanned pit. They're already aware of that. And these are two instances as to which the swivel head itself malfunctioned. So this swivel head was used too many times in the center photograph that you see, or they found a very large boulder, in which case the pipe bursting equipment simply is not going to push that away, and it becomes another excavation point. Pete, you want to come on and talk about the data logger pretty quick?
Sure. Great job, Alan. So as far as risk mitigation goes, Alan and I were thinking the data logger, what a great opportunity to control the downside. And that is, hey, what are those fusion techs doing when the inspector's not available, not paying attention, not there, or you've only got one site visit a week? What's going on those other 4 days? The data logger can keep track of what's going on with fusions when no one else is around. So we could spend an entire hour on that, but Alan, why don't you finish on resources? And I'd just like to say to our audience that we've answered over 110 questions. We were able to keep up with you guys, but if you have more questions, contact anybody on the screen right now. One of the things Dan Landy does for the PE Alliance is keep track of and work on your projects, helping you along the way to make those projects go a little bit better. Alan, let's take a look at some of the resources the Alliance offers.
Sure, Richard, Rusty, Nick, come on too as well. Again, Peter hit it right on the nose there. These webinars are made so much better based on all of your questions that you go through. And yes, we love to talk about high density polyethylene. So definitely share your stories. And here's all of our contact information. Screenshot this so that way you can get any one of us to talk about your polyethylene story. Any final questions while I'm just showing what is available to everybody? Richard, Rusty, Nick.
No, I don't really have any. The guys kept us pretty busy, pretty busy on the time. And Peter, I apologize in advance. I forgot to put my initials on the answer. So any ones that don't have initials, those are mine. No, but I just want to again thank you guys a lot for participating in this. We still believe that education is still a very, very important aspect of high density. Although we've been around for a lot of years, we still find things that are kind of outdated, but again, it's just what you know is what you know. And we're more than happy to help learn. And don't sit there and scratch your head for long periods of time. Just reach out to us and we'll take care of your situations as best we can.
And I don't think you can underestimate the resources. I mean, we've all been in, I know I've been in this 34 years. I think Richard's got a lot of years. Our associates with our companies, they've all have quite a bit of experience. So if you do have questions or concerns or curious about something, please give us a call. Let us know what your question is. Be happy to help.
Yeah, I'd echo that. Any questions at all, feel free to reach out.
Yeah, thank you, Nick. Great job. Alan Ambler, good job. Sign up for another webinar at pepipe.org. Robin Cruz, Sean Scully, thank you so much for allowing the Alliance this opportunity to speak to your members. And with that, I'll say so long. We'll see you next time, next week on the Ask Me Anything webinar at the Alliance for PE Pipe. Thank you again, ASCE, and for our guests today.
Thanks, Peter.